So try it.
That's why I said maybe you have some.
It shouldn't work here. It should work here. Okay? I want it to be onset here in this automaton. I want to find a good state in my cycle. I want to include the accepting state in the cycle. It should work here, but not there. Okay? So, obviously that doesn't work. Okay? Let me get rid of these. Okay? So, how about this one?
But bigger if you go out of the quick state and smaller together.
Let's do it here. Okay? So, I'm going out of a non-accepting state. Okay? That was something like this in the emptiness check. Yes? Again, this. Again, this.
Wasn't one different.
Okay, which one was different?
This one.
This. Okay? So, what is the exact law?
Sorry.
For each of them? This one. Okay? And forget about this one. Does a ranking function exist? Yes? For this automaton. Does a ranking function exist? It doesn't matter if I use less or equal or greater or equal. Okay? As long as I can get out of the accepting state freely, I can find the accepting state in the cycle. Okay? So, let's see. Rank is decreasing along the edges, or rank is increasing along the edges. Okay? Rank is free when leaving and accepting a state. Okay? Do consistent values exist? Okay. Give me rank for each state of this automaton. Rank this automaton.
0, -1.
This one is 0,
-1, -2. -500.
this one 0 again.
Yeah.
Okay? Apply the constraints and as simple as this. How about this one?
No go.
There's no go. Okay? As easy as this. Okay, that was a piece of cake. Okay. Exactly. Where is the piece of cake, you mean? Okay. This is the constraint system. This is the first order constraint system. I'm going to break it down one by one for you. Okay. Initial state of the system or initial state of the product automaton is always reachable and it is marked on the accepting path. Okay. Then if the source state is on an accepting path, okay, then the destination state should also be marked to be on an accepting path, only if we can find an interesting loop emanating from it. What is the interesting loop in our case? Okay, that's it. So, these are the results. Okay, bounded synthesis, if we are going to synthesize this LTL specification, we will end up with this system, and bounded synthesis will give you the optimum system in terms of size. Okay, and this is it. You end up with a system like that. And for non-vacuum synthesis, if you give it the same LTL specification, it will try to find out interesting business formulas for that LTL specification, enumerate all of them and conjunct them as an existential path formulas with the original universal path formula and search for the better system, higher quality system, and we will end up with a system like this. Okay, so we already know that synthesis of this A phi is psi resulting higher quality design. But the question is, can we do better? We found out one equal system. We found out we synthesized a slightly better system, but can we do even better? That's the question.
But now you actually required to add things to the specification. Isn't that exactly what you wanted? Not to have?
Beg your pardon?
No, well, now you were somehow required to add something to the specification.
Yes.
You said we were lazy and we didn't know how to do this.
Exactly. We were lazy and we didn't know how to get the system or make this specification complete. Just added, okay, from the specification itself, we figured out something else and we added it to the whole specification. Okay, we made it complete. But the question is, right now, can we do it even better?
So what are the different vacuous like substitutions you try? The implication and anything else?
Anything.
Oh.
Given any specification, you can try anything.
I mean, so you could get two different better systems from one.
Yeah.
And how would you then compare the two different better ones?
Let's wait.
Okay.
Let's wait a little more. And antecedent failure is a case in point for vacuity and how the systems and model checking and synthesis would suffer from the vacuity concept. But okay, let's see how can we do it even more interesting, in a more interesting fashion. Okay, beyond classic vacuity, till this, okay, everything was done, at least in the model checking. And we only did this existential quantification in synthesis. Okay, there's nothing major. But from now on, you're going beyond classical vacuity or beyond vacuity. Okay, this is our specification. This is the witness formula of this specification with respect to key. And this is the strengthened version or the negation of the witness formula, the strengthened version of the specification with respect to key again. Input is the key, output is the secret. This is M1 and this is M2. Which model is the better model? By common sense, which model is the better model?
M2.
M2 is the better model. How much?
7.
7! Slightly better.
5/7. I got a little arithmetic skill, that's a lot.
So, that's a slightly better. Upon receiving, okay, as long as it doesn't receive the correct key, it won't reveal the secret. Upon receiving the first correct key, it will reveal the secret no matter what. Okay? This is like pseudo command in Linux. Okay? If you
Yeah, it will start revealing the secret.
yes. So M2 is better than M1. And how can we formalize that? Okay. Let's see. M2, first of all, we want M2 to be as non-vacuous as M1. Okay? We don't want M2 to be worse than M1. Okay? So, what do? We would say M2 is as non-vacuous as M1 if all input traces of M1 that are non-vacuous, okay, of M1 that are non-vacuous. All input traces of M1, all pi of M1 that satisfy this witness formula, okay, are also included in M2, okay. that makes M2 no worse than M1, okay? Or as non-vacuous as M1. Okay, so there's no, apparently there's no non-vacuous trace in M1 that makes M2 as non-vacuous as M1. You cannot give a system which is more vacuous than M1, which is worse than M1, okay? So basically, with the antecedent failure, we use the antecedent failure, okay? We use vacuity to tackle vacuity. M2 is as good as M1 in the first place. Okay, what makes M2 less vacuous is at least a trace that is handled non-vacuously in M2. At least one trace in M2 will satisfy the Witness formula, and it doesn't satisfy the Witness formula in M1, but it satisfies the strengthened version of phi. Okay? So, let's see. This path in M2 will satisfy the Witness formula, and the corresponding path in M1 will satisfy the strengthened version. Interesting, isn't it? So, M2 is a strictly less vacuous than M1, but it is a slightly better.
Actually,
Yeah.
from a practical point of view, you could even argue that N1 is better because somehow N2 hides the error, and you will only you might think, okay, my system M2, all right, I tested this and I tested that, looks good, let's ship it, and then there's this hidden factor.
Exactly.
So
That's robustness. So, robustness.
the first one, both are somehow bad, right?
Yes. Both. Okay.
One hides it, and the other.
That would be the conclusion of this talk. Okay.
No, no.
I think-
The secret has been revealed.
I think you need a system that
Right.
automatically whips the person
Yes.
writing bad specifications.
We already knew this concept vacuity and robustness with respect to inputs are the exact dual, the exact opposite sides of a coin, but we couldn't relate them up until now. Okay, right now we've got the formalism to relate to them. Okay, so M1 is good in some sense, in some other sense, M1 is bad. Okay, it really depends on the point of view and the designer's intention. So the synthesis approach would be an interactive approach that in each step will provide a system and ask the user, is this your intention? If not, you can go toward a less vacuous system or toward a more robust system. Okay? So, but here we are talking about vacuity as the quality measure. So M2 is a strictly better than M1, okay, in terms of vacuity as a quality measure. So, okay, that makes M2 the better system. But is it the best system? We've got the M3
Are they
right now.
necessarily comparable?
No, but these two are comparable. So, is M3 as non-vacuous as M2? You tell me. Is it? Okay, let's see. Okay, all non-vacuous traces of M2 are included in M3. This path, okay, is also there. So that makes M3 as non-vacuous as M2, okay? But what makes M3 a strictly less vacuous? You tell me.
Trace key and
Give me the trace.
The only difference, I guess.
key not
Key, not key, okay? That's the prefix of the traces that makes M3 strictly better than the M2. Exactly. So M3 is the best system. Okay, let's continue and see how we can synthesize it. A least vacuous system. We are going to work the least vacuous system. Given some model and some specification, we would like to synthesize another model such that the next model is less vacuous than the given model. Okay, so if you've got this, okay, in model checking, if you model check your system and turns out to be that model turns out to be vacuous, then you can give it to our synthesizer and it will spit out a non-vacuous model for you that satisfies the same spec. So let's see how can we do it. Okay, first of all, M prime and phi prime are M and phi with fresh output literals. This is the example. Phi is globally key implies eventually secret. Phi prime is globally key implies eventually secret prime. Okay, so then we would do this. Okay, M1 is a strictly less vacuous than M2 if and only if this product, okay, this synchronous product will satisfy this formula. This blue part says M2 must be as non-vacuous as M1. That means all witness traces of M1 should also be included in M2. Okay? So that red part makes M2 a strictly less vacuous. Okay? That says, okay, there exists one witness trace that does not belong to M1, but it belongs to M2. Remember, M1 prime is talking about secret prime, okay? So basically phi prime and phi, not phi prime, okay, belongs to M1, and phi psi, okay, belongs to M2, okay? That makes M2 a strictly less vacuous. So you're equipped to synthesize the least vacuous system with respect to this witness formula, and we can easily extend it to several witness formulas. Okay, interestingly, we can synthesize a least vacuous system for a given specification, okay, via formulas of the form A phi and E psi. So that's an iterative approach. In the first step, you will synthesize a system from nothing. In the second step, you try to make it less vacuous, till it is unrealizable. Okay, the last system you got is the least vacuous system that will satisfy the specification. Okay, let's see some examples. Okay. Yes.
How is it so physically it is done by looking for a trace that, I mean, this existing trace that exists only with M2 system, but it doesn't exist in M1 system. And then out of this trace we create transitions.
Okay, that's easy.
No, is it like this? Like that's
No.
no?
That's even easier than that. This M1 prime, I will produce a product automaton of this M1 prime. This M1 prime is actually given.
Yeah.
Okay. I will do the synchronous product of this M1 prime and the Buki automaton. Okay, I've got, and then I would ask for the SMT solver or the synthesizer. Is there a symbolic model, namely M2 here, okay, of certain size, okay, that will do this, okay, that will satisfy this implication and this conjunction. So basically, N prime is also included in the automaton.
How do we know the certain size that we ask for?
We don't know. We would search from the beginning, or we would search from the size of M1 to our outputs. Okay? And the other thing, the beauty of this approach is we are actually using one of the advantages of bounded synthesis. I already told you that in bounded synthesis, it's no need to determine the Gucci automaton. Okay, so if we compute the synchronous product of a Moore machine and a Bucci automaton and non-deterministic Bucci automaton, it would remain a non-deterministic Bucci world automaton. So that's why bounded synthesis is interesting for us. So that's as easy as that. Piece of cake. But where is the cake? Okay, this is the partial specification we had yesterday, and this is the system. I don't know if you came up with it or you came up with this system that toggles